Let me start. Hi, everyone. Welcome to the C3 AI DTI seminar series. My name is Gauri Joshi. I'm an associate professor at Carnegie Mellon, and I'm co-organizing and co-hosting this semester's seminar series with Professor Richard Zhang, who is an assistant professor at University of Illinois and who is also our speaker today. C3 AI DTI features research that focuses on artificial intelligence, machine learning, and big data, and studying how these can lead to scientific breakthroughs with large-scale societal benefits. Before we begin, we would like to pause to acknowledge the support of our academic and industry partners, for which we are deeply grateful. Our fall 2022 series was organized around two themes, adversarial machine learning and distributed and federated learning, with alternating talks on each of these themes. So we are almost wrapping up for the semester. We have our final two presenters, Richard Zhang today and Siwoong Oh from University of Washington next week. You can also find recorded versions of all the previous talks in this semester and semesters before that online. So please check those out on our YouTube channel if you're interested. So today we are very happy to welcome Professor Richard Zhang, who will share his research with his talk entitled Improved Adversarial Attacks and Certified Defenses via Non-Convex Relaxations. Richard is an assistant professor at UIUC in the Department of Electrical and Computer Engineering. He received his SM and PhD degrees from ECS MIT in 2012 and 2017, respectively, and he was a postdoc at UC Berkeley after that. His research is on optimization and machine learning, with a particular focus on building structure exploiting algorithms to solve real-world problems with provable guarantees on quality, speed, and safety. He received the prestigious NSF Career Award in 2021. So without further ado, let's welcome Richard. Let me stop sharing. The talk will be 50 minutes long, and for the audience, you can use the Q&A feature in Zoom to submit your questions, and we will ask them on your behalf at the end of the talk.
All right, thank you very much for the introduction, Gary. Can you see my slides okay? Can you hear me okay?
Yes.
Fantastic. All right, thank you very much. I'm very happy to be here today to talk a little bit about improved adversarial attacks and certified defenses via non-convex relaxations. So this is work with mostly with my student Hongming Chu, who is a co-author on this paper, and the QR code is here in case you're interested in reading the paper. So adversarial attacks, we all know what that is, but just to make sure everyone's on the same page, the idea is that neural networks are they're very good at classifying pictures of cats as cats and dogs as dogs and bicycles as bicycles, but for some reason, when we perturb them just by a little bit, by adding a small amount of adversarial perturbation, we can get them to essentially classify whatever we want to. And it's a very scary idea if we want to apply this to something perhaps in a safety critical environment. And so to make neural networks resilient to those kind of attacks is actually a very well-known strategy at this point. The idea is to just, well, here's a picture that looks like a cat to you and me, but it's classified as a bicycle, so let's just put this picture back into my training set and label it correctly as a cat, right? So I just keep training, I keep attacking it, I keep getting pictures of cats that's been essentially mislabeled as a bicycle by the neural network, and I'm going to go and relabel, and when I keep doing this, right, it actually works really well, okay? So if you just train a neural network and, for example, on MNIST, it's very easy for an undergraduate researcher, right, to get 99.8% accuracy, but as we know, if we attack with adversarial perturbations, then it was just a very small amount of perturbation, you can get a horrible training, horrible testing accuracy, right? So just by a slight amount of attack, the classifier becomes essentially useless. So with the strategy of putting the attack back into the training set, what we discover is that, well, okay, so we will lose some amount of accuracy. We don't get this robustness for free. So here, perhaps with MNIST, you stand to lose about 1% accuracy. But now when you attack it, right, you're able to mostly survive the attack, 89.3%. Perhaps that's good enough for some application with recognizing digits in actual postal services, etc. Right. So this really does work and works really well. And but there's always a possibility, right, that you can come and there's a future attack that could break you, right? All you've done at this point is simply to say, hey, I've trained my neural network to be progressively more able to withstand the attacks, but we don't know, right? So this was something that the original authors of this paper, Madria, also thought about, and they actually opened the neural network up to attack. So they said, okay, we could get 89.3% accuracy, but perhaps worldwide, there's some researcher out there who's able to break our model and is able to get a lower accuracy, is able to attack our model successfully. So we weren't able to do that with our own attack, but perhaps someone in the future is able to develop an attack that's strong enough to break this model. So the accuracy without an attack is 98.8%. The authors themselves were able to get it down to 89.3%. With the sorts of attacks that they had developed. And after opening this up as the MNIST challenge, right, to the world, we saw a progression of attacks, and it became less and less accurate as more and more powerful attacks were developed. And the challenge started in 2017, went through 2018, 2019, 2020, 2021, at which point the authors of this original paper concluded the challenge. And we do see a drop in accuracy, right? So 89.3% went down to 88%. But I mean, that's still pretty good, right? That's still pretty good. At this point, after 4 years of penetration testing, I'm fairly comfortable putting those in perhaps a real world system in which I have some other error checks, etc., just to make sure. 88% is pretty good, right? But what would be really nice if we could really come up with a conclusive formal proof, right, that actually the accuracy will not dip below, say, 87%. It seems like that's a realistic statement to make, right? So can we come up with a rigorous formal proof, a formal mathematical proof that the accuracy won't go down? I mean, it seems to be true. And this is an idea that's also been around for a while now, and this is the idea of verifying the robustness of a model, perhaps after you've trained it adversarially. And the sorts of techniques, and we'll go into this talk is mostly about these techniques, right? So there's something called convex relaxation. So at this point, we just want to just call this a mathematical technique that delivers a provable lower bound on the accuracy upon attack, right? So 88.00%, I promise to come up with a percentage that lower bounds the worst case attack from any possible point in the future, any possible attack, right? I promise to come up with a lower bound that will never be defeated, right? So the state of the art today, when you apply these strategies, yeah, I mean, we ran all of the state-of-the-art codes, and we've got about maybe 30% if we squint a little bit here. So you get this massive gap, right? Like 60% now. I mean, 30% accuracy at this point, this is not really usable, right? And no real-world system can tolerate your accuracy dropping from around 98% to 90% down to 30%. So what's going on? I mean, the two possibilities, right? So the first is, okay, so if there does exist an attack at some point in the future, then of course you'll not be able to certify it because that's false, that's not correct. And maybe there exists an attack in the future that would actually drive the accuracy down to 30%. There's another possibility, the most likely possibility is the model is already robust. The minimum accuracy you can hope to achieve is something like 87% maybe. but just this proof is not very good, right? And it's conservative, right? And I just want to mention at this point, right? This is a tiny model. It was trained on essentially an undergraduate data set, MNIST, perfectly clean, perfectly labeled, and underwent 4 years of white box penetration testing. And I mean, at this point, it's I would say it's unlikely, right, that this model is still vulnerable, but we still don't know, right? I mean, it's unlikely, but we don't know for sure. It's still inconclusive. And now we ask the question: is it really realistic that we take, you know, a neural network trained on a much more sophisticated, much bigger data set? Can we open it up to 4 years of white box penetration testing worldwide to see if it's really robust, right? Can we really do that with some of our classifiers for more security critical tasks, for example? So that's a very worrying proposition. So there's been then ongoing work to ask, okay, so we think probably the case is that this proof is just not very good, and with better techniques, more sophistication, we stand to perhaps increase that 30% up to some number closer to 87 or 86 or 88, right? And so there's been this ongoing work, and I mean, these proofs are very difficult to construct, and so a particular set of authors here shown on the screen, they set up a smaller MNIST network with very similar training environments as the previous paper. When you attack those models, it goes down from about 96% down to 84%, so roughly similar numbers. And they constructed a proof that is robust up to about 38%. So what they actually found is, okay, so there's this 45.73% gap, and then they try to optimize this gap to reduce it as much as possible. And they actually found that using existing techniques published in the literature, their technique unified all of the previous techniques, and that by optimizing their technique, they got stuck on a 45.73% gap. So they're basically saying it's actually not possible to get beyond this, right? So even though our model is probably 80% accurate, robustly accurate, and it probably is rigorously 80% robustly accurate, we'll never be able to prove it using existing techniques to better than 38%. So 38%, that's really, really bad. Maybe this technique is just certifying, this whole idea of certifying using convex relaxations. Maybe this is a hopeless direction, right? This will never be useful if you have a gap that's 50% large. This technique might have serious troubles. So in this work, I'm about to talk about, what we managed to do is to actually reduce this gap down to 5%. Okay, so really the key idea is we came in here and we said, well, if you have a convex relaxation barrier, can we overcome this convex relaxation barrier by using a non-convex relaxation, right? So a non-convex relaxation will not be subject to the convex relaxation barrier. There's a lot of issues that we have to overcome to make this idea work, but we managed to make this work and reduce the gap down. And we think with refinements of this technique, we can hope to perhaps squeeze it down to 1 or 2%. I don't know, but we hope we can do that. Okay, so this is an outline of my talk. So what I like to do is I like to go through and actually talk about why we have this convex relaxation barrier before we actually talk about how we're able to overcome it using some of this non-convex relaxation ideas. Towards the end of the talk, I'm going to briefly talk about some of our work in the algorithm side of actually solving these non-convex relaxations, but most of this talk will be dedicated towards section 2 here, which is the actual relaxations themselves. And finally, I'll conclude with some outlook on some future work. Okay. So before I talk about the adversarial machine learning problem, I just want to kind of broadly talk about convex relaxation as it exists in the wider world. So convex relaxation, my group and I, we've had a lot of experience working with it. We managed to use this idea that is actually very, very old. We used it to solve many industrially important problems to near global optimality in near linear time. So my sort of bread and butter is electricity networks. And here there's a particular dispatch problem, and we're able to use convex relaxation to solve it to 99% optimality in less than 3 minutes for the entire European power system. We apply this to the optimization of the timing of traffic lights, and using convex relaxation, we're able to optimize all of the traffic lights throughout the entire city of Los Angeles. We apply this technique to learn graphical models for brain connections, functional brain connections, and we were able to learn models with greater than 92% true positive rate and 0% false positive rate in about 22 minutes, also on a laptop computer, right? So going into this problem, we were quite optimistic that perhaps some of the techniques we have for convex relaxation, we could just apply it and maybe improve upon this existing state of the art. So initially looked at this problem, looked at some of the existing literature, and it's okay. So let me tell you, our previous work were primarily based on this idea of a tree-like graph. So in electricity networks, for example, but also road networks, you have a structure in which there's an underlying graph that represents the system being optimized, and the graph is not random. It has a very specific structure that looks like a tree. And if you cluster the nodes together, it really looks exactly like a tree. And actually, people have been optimizing it in this manner, right? Because the network changes very slowly, transmission lines get built very over the course of decades. And we took some of the ideas that people use to heuristically optimize power systems and made it rigorous with notions of tree width, tree decompositions, and partial separability. So we proved the theorem, and the theorem said if you have a network and the network looked like a tree, okay, so if it looks like a tree, I can guarantee you that I can solve a convex relaxation that's very good in near linear time. So with this result in mind, we sort of asked, can we apply this to the adversarial machine learning problem? And it doesn't work. Okay, it really doesn't work. So really, when you come to these problems, and if they're convex, then you can be quite sure that these sort of one-size-fits-all techniques would continue to work for every single problem. Unfortunately, the situation here is that this is a non-convex problem, and every non-convex problem is a little bit different. Neural networks are graphs, they are networks, but they're not really tree-like graphs, and so the structure doesn't really work. So we had to come into this problem and ask, is there a different structure that we can exploit in order to make any progress on this problem at all, right? So what kind of structure is there? So let's ask the question, why do there exist adversarial examples in the first place? So this point here might be the input image, it might be a picture of a cat. And what we want to do is we want to perturb it by a very small amount and get the neural network to misclassify, right, as the picture of a bicycle, for example. And here, the perturbation on the image is a convex set, a box in this case. But the neural network parameterizes a decision boundary that's nonlinear. The point of a neural network is to parameterize a nonlinear decision boundary, right? And it normally does it well to separate pictures of cats and bikes, but here we have a picture that for some reason is very close to the decision boundary and could be misclassified as a picture of a bike. So this is in the image space, but the classification actually occurs in the feature space, right? So we feed this image into the neural network, and at the very end, at the very last layer, essentially, we get a set of features, and the set of features has a linear decision boundary, right? And on one side of the linear decision boundary is all the pictures of cats, features of cats, right? On the other side, all the features of bicycles. And the trouble here is, right, your input, which your input set, a convex set of attacks, is now a non-convex set, right? And so we're not too sure whether there actually exists an image that is close to the input in the original image space that would poke into the decision boundary in the feature space. So how do you find this adversarial example is, well, you go in here and you solve an optimization problem. So here I rotated the image so that we can see our goal is to find a point as far down as possible. And we might actually formalize this by the idea of optimizing a cost function. In this case, cost is just pointing upwards. So we want to optimize going downwards. And so we pose it as a mathematical optimization problem. Here, all this is saying is we want to minimize the direction going downwards and U is the feature produced by the model with the image as an input. And the image is going to be so much far away from the original image, which I denoted here as x hat, right? So this approach can obviously find a local minimum that does not misclassify. And so you have to run it over and over and over again. Standard techniques, gradient descent, projected gradient descent, and eventually, hopefully, you land in this well here, and this well causes misclassification, and you found an adversarial example, right? So how you find adversarial examples is you just go in here, you run an optimization problem, you run gradient descent, and you just start over and over and over and over again until you hopefully land in the well that's the global minimum that is an adversarial example. So another way to view, if you don't have any adversarial examples, right, if we now shift the decision boundary a little bit further downwards, so this model is now robust, right? So what does it mean that this is robust? Is, well, the same optimization problem of trying to find the bottommost point, right? The point as essentially trying to cross over the decision boundary. We can optimize in this direction just like before, right? We have this cost, which is up and down, and we just want to find the southmost point, the bottommost point. I mean, we could get stuck, but there exists a global minimum, and that global minimum defines what we call a robustness margin, right? The distance of this point from the decision boundary. And if this distance here is positive, well, actually you prove that the model is robust, right? Because, well, then you cannot get further into the region where you might misclassify because, well, this is already by definition the global minimum. But if you cross over, right, if the robustness margin is 0 or negative, then then you have found an adversarial example. So this is actually the same problem as before, but now we formalize the idea of looking for an adversarial example as an optimization, and also we define this number by which we can hopefully use this to determine whether this model is actually robust, right? So how do you certify robustness is to rigorously show that your robustness margin is positive. So every method is based on this idea, okay? So one way you could do it, right, is you can try to form a convex shape that encloses the shape that you have here, right? So here I've shown a convex shape, a box, and then now I have a convex shape. You can easily find the most potent attack, right? The attack that is the southmost on the diagram, here, the bottommost point of the diagram. That's very easy to do. It's a convex optimization problem. We can pick up a standard textbook, and then we can find this point here. You can find it using gradient descent, for example. And we find that this most potent attack from the convex set is actually already robust. This is not going to cause misclassification. So here is a subtle point that this attack cannot actually be realized because it doesn't lie in the original set of possible attacks, but it doesn't matter because our greater convex set encloses our set of possible attacks. And so this greater set of attacks has no viable attack that's going to cause misclassification. Therefore, our model is going to be certifiably robust. So this is the entire idea of convex relaxation, that I get a set of non-convex attacks. This is just naturally the case in the feature space, and I enclose that within a convex set. And I can optimize over the convex set and look for the worst, the most potent attack. And if that attack does not cause misclassification, then certainly my realizable attacks will also not cause misclassification. So this picture is what we hope to achieve. Unfortunately, oftentimes what we end up getting is that we're going to get a convex relaxation that looks like this bowl, the circle here. And what we see is that when we optimize it, we get a point at the very bottom. And what that says is, okay, the worst possible attack, right? It can cause misclassification within the convex set. So there's a subtle point here now becomes important, right? Because even though there exists an attack within the convex set that causes misclassification, you can't make this attack happen using your attack budget, right? It's not physical, it's a fictitious attack that we introduced in making this convex relaxation. In relaxing the set of non-convex attacks into the set of convex attacks, we have introduced fictitious attacks that cannot be realized. And this is an example of a fictitious attack that cannot be realized, but would cause misclassification, right? So here, right, it is true that our convex relaxation gives a lower bound, right, on our true robustness margin, but at the same time, this convex lower bound is now negative. So it doesn't tell us anything, and we cannot be sure, right? We cannot be sure that there might or might not exist a point within the original non-convex set that crosses the boundary because it looks exactly the same in both cases. So we're not able to make any conclusions, and here, well, here the method just catastrophically fails. So a natural idea to follow is, okay, well, this set is really, really big. Can you make it tighter? Right? Can you shrink the size of this set? So here, very unfortunately, we get into the situation where if we're strictly working with bowls, bowl shape, circle shape, convex relaxations, then there exists no convex relaxation that is both correctly a convex relaxation, right? It doesn't have any part of the non-convex shape poke out, right? It truly is enclosing the non-convex shape, but at the same time, it's the smallest possible. It will always exceed this point here and cause misclassification. So we cannot actually tighten this bowl anymore to make a guarantee. In other words, this bowl shape is not expressive enough to actually capture the true underlying shape of this non-convex set of attacks. And so if we try to use a bowl as a convex relaxation, then we will never, ever, ever be able to certify the robustness of this classifier, which actually is robust. We're never able to develop a lower bound that's positive. But that does not mean that the model is not robust. It just means we reached the fundamental limits, the convex relaxation barrier for this particular type of convex relaxation. Okay, so this is one possible outcome when you have a convex shape that's too simple. So you're already thinking, right? Okay, so this shape is too simple. Of course, nobody will use a bowl, right? That's way too simple. How about a polytope, right? How about polytope is also convex. Polytope is actually one of the first things we introduce in a convex optimization course. And indeed, right, we can form what's known as the convex hull, which is essentially the smallest convex shape described as a polytope that's going to enclose your shape. And you optimize over that, you're guaranteed to you're guaranteed to find the globally optimal, the most potent attack in the original set, right? So if you can construct this, then you're able to overcome the convex relaxation barrier. The trouble here is, in order to get even to probe at the convex hull requires you to make what are known as cutting planes. And this is actually the technique that shows up in algorithms called branch and bound, branch and cut, used to solve mixed integer linear programs. They introduce these cuts, they progressively refine these shapes by adding in more cuts, each cut being another plane, another face. But in the worst case, you can expect to add an exponential number of faces or corners, and you're able to get to the convex hull only by paying a price of exponential time, memory, etc. Right? And once you found the convex hull, in order to try to get the most potent attack, you also have to look at an exponential number of faces. So yes, this would theoretically work, but in fact, constructing the convex hull is harder than solving the global optimization problem. And so this is not realistic, right? So there are two sides to the barrier. On one side is the expressiveness, but on the other side is you can find a very expressive convex shape and it will be completely impossible to construct it in a reasonable amount of time to be tight enough to be useful, right? So there's two sides to the same coin. So here now, obviously, the title of the talk is non-convex relaxations. Well, it seems like obviously if you come up with a non-convex relaxation, then you'll be able to easily overcome these two issues, right? And non-convex shape can both be very, very expressive and also very, very simple, depending on how we choose to express the shape. We're no longer bound by the constraints of convexity, which is actually an extremely, extremely strong condition. Once we throw away convexity, it seems like then we can come up with a non-convex relaxation very easily. So the trouble here is, okay, now you have a non-convex shape, right? And you can heuristically find the globally optimal point, right? The globally optimal point might be here, but you really don't know that it's globally optimal. You could also get stuck at this point here, and locally it looks the same as the globally optimal point, right? So a sphere's local minimum now looks the same. And in general, you have no way to distinguish a local minimum from a global minimum. So you cannot give a proof that you have actually found the bottommost point, the most potent attack. So you might find an attack and conclude that, okay, so my attack is not going to cause misclassification, therefore the model also isn't going to cause misclassification, but that's not true because there exists another attack within the non-convex relaxation, right? That's going to potentially cause misclassification. So here we are bounded by the fact that we cannot optimize over the non-convex shape. So just to briefly summarize at this point, what we want to do is we want to construct some kind of relaxation, find the most potent attack. We take the original non-convex shape of attacks, and we relax it into a convex shape of attacks or non-convex shape, right? And we find the most potent attack within that set. And if that most potent attack is still not potent enough to cause misclassification, then we're done. And if we can prove that, then we provably guarantee that the model is going to be robust, right? But the trouble here is the relaxation needs to be expressive enough to actually capture the contours of the set of non-convex set of attacks. And here, for example, the ball is just too simple. Even if you tighten it to its optimal tightness, you cannot prove robustness. A complicated relaxation like the convex hull or a polytope might sound like it would overcome this issue, but then the trouble is you have to add an exponential number of faces potentially. And so the relaxation needs to be simple in sort of the sense that you can still execute it in polynomial time, ideally linear time, right? And you can easily come up with techniques that are convex, and you can get an arbitrary tight solution if you're willing to pay exponential time. And if you're going to throw away convexity, then all of a sudden you can't prove global optimality. And so you need a relaxation that's easy to optimize, but after you optimize it, you need to prove that you're at the globally optimal point. And this is the core issue with just a general non-convex relaxation that you pull out of a hat. You can optimize it, but you can't prove that you find the globally optimal attack, and so you can't prove that the original neural network was not robust. So here now we arrive at this point here. We've seen what the issue with the convex relaxation barrier is. What we need to be able to potentially overcome it, we need something that fits 3 criteria. And now let's look at how we might go about constructing a relaxation that could actually hit all 3 criteria. So we begin with a paper that came out in 2018 at NeurIPS. And this paper finds that this particular problem of computing the robustness margin, right? Let's just recall what it is. It's just I minimize the distance to the decision boundary subject to my feature being here. I put a one layer, right? A one layer neural network just for argument's sake, and that the input to the neural network is within some distance away from the original image. So this paper pointed out that this condition of taking the maximum of either alpha or 0, beta is equal to alpha to 0, can be written as 3 smooth constraints. So the first two constraints, beta is greater than alpha, beta is greater than 0, it's really just beta is greater than the maximum of alpha and 0, and this is linear. This is the easiest constraint you can possibly construct. And the third one here is to say that, well, if it's greater than alpha or it's greater than 0, we only want one of these two conditions to hold, and so we can multiply the two together, and one of them will be 0, right? One of them will be 0, and that enforces that beta is actually equal to max of alpha and 0. So this looks very complicated, but really the idea is that this is a linear constraint, this is a linear constraint, and this is a quadratic constraint. So I can take this problem here in which this just looks like a fairly unstructured arbitrary problem. And what this paper showed is that using this insight, we can just go ahead and rewrite the same problem as an optimization problem in which we're minimizing a quadratic function over a list, over a vector, essentially, right? A quadratic function subject to quadratic inequality constraints. Actually, there's some equality constraints, but let's just ignore that. It's a very subtle point that doesn't change our arguments here. So we can just think of this original problem as a quadratic minimization subject to a quadratic inequality constraint here, right? And once you write it in this form, you discover that there's a lot of literature on this particular type of optimization problem. I just want to pause here and say the dimensionality of this problem is also linear with respect to the actual attack problem that you had originally, right? So the number of things you have to optimize in this quadratic minimization subject to quadratic constraints, right? Quadratically constrained quadratic program is number of input channels. So here, for example, mnist 28 squared plus number of activations, right? And the number of constraints is going to be 3 times the number of activations, roughly speaking, right? So this is linear, everything's good, but this is non-convex. What this paper evoked is actually a very classical idea, something called STP relaxation. We can come in here and recognize that this term here, Z transpose CZ, is in fact the trace of Z transpose CZ, and that the trace has a cyclic property that I can move the Z transpose over to the other side, and now I can define a new variable Z, big Z, that captures the effects of ZZ transpose. So I define a new variable to contain all of the quadratic terms ZZ transpose, and then I notice that the constraint that Z is equal to Z transpose can equivalently be enforced as the condition that Z is positive semi-definite and Z has a rank of 1. So if we just substitute all of these conditions back into the problem, we end up rewriting this original problem as a particular optimization problem in which you have some linear constraints over a matrix Z, you have some linear constraints over a matrix Z, and the Z has to be positive semi-definite and has to be rank 1. Okay, so if we just delete the rank 1, because rank 1, I'm not sure what that constraint really does, let's just ignore that. If we delete it, then we find that, okay, well, linear constraint, linear objective, and a set of positive semi-definite matrices. If you read Boyd and Vandenberg, you find, okay, well, that is a convex set. So if I just delete this constraint, I get a convex relaxation because it has fewer constraints. Right? So you run this and it's fantastic. This original paper recorded phenomenal numbers, but unfortunately, solving this problem is ridiculously expensive. It's so expensive that even a toy example you will not be able to solve. Right? So to give you an example here, mnist 28 by 28 input image with 200 activations. Your N, your list of numbers to optimize is about 1,000, which is not that much. But here you're optimizing over 1,000 by 1,000 matrix. So 1,000 by 1,000 matrix is going to be 1,000,000 elements. So you think about the cost of training a 1,000,000 parameter neural network, right? So that is the cost of solving this, right? So it's very, very expensive for just a toy model that would be no good in practice, right? So even Jan LeCun's neural network from 1990 would have an N of 10,000, for example, and it would be 100 million. It would be really state of the art to actually optimize this. So that is the scalability is a game stopper, a showstopper. It just prevents us from really seriously taking this idea. So here we want to pause and ask the question, okay, so scalability aside, all right, let's just put that aside. Why is it that this relaxation is so good? Why is it so much better than all the other ways in which you could construct relaxations? So I like to sort of answer this question by showing this diagram here. So just suppose that your set of attacks is contained in these two lines here. Okay, so in practice, it's going to be some high dimensional shape. But just bear with me while I say that it's contained within these lines. Then what a semi-definite relaxation does is it fills the area between the lines to construct a convex shape that looks like this here. Okay, and obviously, if you optimize over this convex shape, then you end up with a guarantee that then goes back and is applicable to the original problem here is actually equal, right? So this is exactly tight. But the key reason why it's able to be exactly tight, right, is because the original set is placed at the boundary of the relaxation. So that is the property of the semi-different relaxation that always wants to put the original set at the boundary of the relaxation. Okay, so maybe the optimal point is actually here, right? If we're optimizing to the left, and here this would not be tight. It would not be a equality for the bound. So it's not necessarily true. It's always tight, right? That's clearly false. But what I'm saying is that it places the original set at the boundary, so you can hope that when you find the optimal point at the boundary, you can hope, and oftentimes it is indeed the case, that then it lies exactly on the original set, and then you get an exact bound. But of course, right, it goes from a line into a filled region, right? And when you look at the numbers, right, it goes from a list of n numbers into a matrix of n by n, which is n squared numbers, right? So this is completely out of reach, but the idea is amazing, but it's just out of reach. We can't really solve it, right? So here, let me propose a very stupid idea, okay? So how about we just hollow this bowl out, right? How about we just optimize over the boundary of this convex relaxation? I mean, it's a convex shape, right? It has a boundary. Can we optimize over it, right? So here you see this shape is very interesting, right? Because if you optimize over that boundary of this shape, it doesn't get stuck, right? It's very different if you start from this point here. I mean, it might go here, but it will get stuck, right? But with this boundary, it also has special properties. It's also not a random non-convex shape. It's a very special non-convex shape, and enjoys the same property that places the original set at it contains the original set, right? Of course, right? But then if the semi-different relaxation is going to be tight, then now we can hope that this non-convex relaxation would also be tight, right? So here, once again, this is exactly equal, but this is now a non-convex relaxation, right? So the key idea is to take the surface, right? Take the surface of the convex relaxation, and the surface is going to have a lower dimension. It's going to have a much lower dimension than the entire interior, which we're not interested in the first place. Right? And so, in fact, this surface has many properties. It's a very, very special shape. It's in fact a Riemann manifold under certain assumptions. Okay, but here this is exactly a Riemann manifold, and the dimension of this is equal to n times r, where r is, okay, it's a relaxation parameter. We're going to come to this in a second, but it's low dimensional. If you pick r to be small enough, it's order n. It's order n, and so this particular problem we can hope to solve with order n number of parameters, right? So order, instead of 1,000,000 from 1,000, we might get 3,000 or 4,000, which we can optimize, right? And that has this property in this case here, right? All local minima are actually global minima, okay? Before we really go into the properties, let's just see how we're able to even formulate it, right? So what we have here is what we've done is we took the original problem and then we rewritten the rank is equal to 1 as rank is less than r. Once we do that, we see that the original problem here is when rank is equal to 1. And if rank z is less than or equal to n, then any n by n matrix is rank n. So this constraint disappears, right? So then the n case here is equal to the SDP relaxation. So if we solve for some phi r where we place a rank constraint of r, let's say 10, then it's actually going to be tighter. It's actually going to be tighter than semi-different relaxation, right? And the other thing is that, okay, so an n by n a matrix that is going to be rank r, we can factor it into an n by r factor and optimize over the factor. And that way we're able to rigorously optimize over n times r or order n variables if r is, let's say, 10. So this is both tight and it's also scalable, right? Which is very, very exciting. Okay, I'm still a bit worried about this global optimality. So here is a very special shape. It's very, very closely related to Riemann manifolds, and there's been some very important work done here. What has been shown is that if this particular set here, which could be arbitrarily complicated, indeed, actually, this has not made the problem easy. In general, this is going to be NP hard as well. But if a point satisfies what is known as the linear independence constraint qualification condition, then you can show that at around that point, the Riemann manifold is smooth. Okay, so then if this is satisfied everywhere or almost everywhere, then the shape is very simple. It's almost essentially a smooth Riemann manifold. And if it's exactly a smooth Riemann manifold, then Bumel, Voronitsky, and Bandera wrote a paper that the journal version dates to 2020, in which they showed that you can actually just globally optimize this non-convex shape, and you can get an epsilon optimal solution polynomial in n and 1 over epsilon time. Okay, so this looks complicated, but really what we're just saying is you're able to globally optimize. This is a shape that in practice, right, R is about 10, and you can actually use this algorithm is going to work, right? Now, okay, the crucial ingredients is that it doesn't need to be smooth. If it's not smooth, it completely fails, right? So really a major contribution of our paper here is actually prove that this particular problem, this verification problem, is going to be smooth. It's going to be a smooth Riemann manifold. Okay, so that's in this paper right here. Just let's see some more detailed simulation results. So what we did was we went and took all of the models that this previous paper, the Salmon et al. 2019, to show the existence of a convex relaxation barrier. What we did was we applied this technique here, which we call it Burer-Monteiro, because inspired by this paper, Burer-Monteiro, and we find that, right, we're able to completely, so LP full here is the Salmon et al. Best possible linear relaxation. And you can see with a radius of, let's say, 1.5, it's now pretty much vacuous. We're able to, okay, there's still a bit of gap, but this is still at early stages. And certainly, once your radius gets small, the Salmon et al. Becomes relatively good. At that point, we completely close the gap, and it becomes very, 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 very tight. How is this possible? How could you close this gap? Right? Well, we're not claiming that we came up with a polynomial time algorithm to solve an NP-hard problem. We're not claiming that. What we're claiming is that, right, as the attack radius increases, as the attack budget increases, right, all relaxations eventually become loose. All we're claiming is that this sort of this non-convex relaxation closely related to semi-different relaxations, right, it stays tight longer, right? It stays tight for greater attack budget than existing techniques here. So you can see that as we increase the attack radius, that existing methods quickly become loose, but we're able to remain tight longer, right? We also eventually become loose, and we must become loose, or else we came up with a polynomial time algorithm to solve NP hard problems. That's not possible. So here, we're just simply tighter for longer, right? We're just tight long enough. And once you go past the decision boundary, it doesn't matter, right? After you go past, you can be as loose as you like, and we can remain tight longer than a previous work. And this is showing the same result for L infinity radius and L2 radius, okay? Let's just go into a little bit more detail as to what the attacks actually look like to show you that both, right, generates an attack as well as certifies the quality of the attack. So here we have MNIST, because the previous models were MNIST. We have an image of 1, and as we know, 1 looks like a 7. So when you do an L2 attack, it's going to try to make it look like a 7. So initially, the classes, right, 1 is 99.7% with a 0.5 attack radius. But we're able to lower bound a difference, a bound that remains tight, right, as the radius increases to 1. And now the previous methods are no longer able to provide a bound, even though it's actually very robust at this point. We're able to also prove that when the model starts being so robust, 55.22%, top one, that is 1, and 43.85%, that it's 7, we're still able to certify, right? With this very small gap now, we're able to still certify that this classification will not make a mistake, right? Which is indeed the case, right? And when we finally go over, right, that you go past the decision boundary and misclassification will occur, even here we find that this lower bound on the difference between 1 and 7 is still relatively good, right? So the amount of misclassification we can still lower bound to very good accuracy, okay? And this plot here is to just show you that, yes, another problem is that as you increase the number of layers, you become loose. And we also become loose because we have to become loose, but we remain tighter longer than existing methods. Okay, so that's the method. And I'm actually already a little bit over time, but just really want to quickly talk about actually solving this non-convex optimization problem here. So we said that, okay, so I simplified this problem a little bit, right? I just wrote it as F, where F is strong and convex. So it's a slightly simpler problem than what we had from before, but the results are very, very similar. Let's just look at this slightly simpler problem. So we have an issue that, okay, so you can optimize it, right? You can globally optimize it in polynomial n, where this is n by r, right? Polynomial n and polynomial 1 over epsilon, right? And gradient descent, you can actually show under some conditions that it gets you n, right? Where this is a polynomial, we're assuming r is order 1. Let's say r is 10, right? So you can get order n, but you need a polynomial in 1 over epsilon number iterations. So as a consequence, you can't get very accurate. You can't get accurate enough for it to be a certification. So it's very, very fast per iteration, but the convergence is too slow. So actually in practice, anyone who uses this technique is forced to use a trust region method. So that's the disclosure. We also had to use trust region, right? In our case, we used the Nitro nonlinear optimization software, commercial software, right? To get an n cubed. And so this was very painful. And this is a problem facing everybody working in this area right now. Okay, but we have some work on this. What we found is that actually, if you just take gradient descent and you just add a term here, a preconditioner, you can choose this precondition very, very carefully. It has a lot of subtle connections with Riemann manifolds and Riemann geometry, Riemann metrics here, that with a careful choice of this eta parameter, we're able to then actually converge once again at log 1 over epsilon, right? So n log 1 over epsilon. We're still in the process of applying this to our certification problem, right? But we believe that this will overcome, and we're now able to actually be linear, both in, right, the number of activations, the input size, as well as the accuracy needed to actually certify. So we believe this is going to happen, okay? We came up with a stochastic version as well. In fact, this is just presented a few hours ago at NeurIPS 2022. The stochastic version here we applied to a different problem, so I don't want to go into too much detail because I'm already out of time. But once again, right, we're able to overcome any problem with here well conditioning, ill conditioning. But this is the reason why gradient descent slows down to sublinear 1 over epsilon convergence rate, and we're able to solve it using stochastic gradient descent as well. So this work, we believe, can be extended, and then we can come up with the SGD, right? But let me just conclude here because I'm already out of time. So what did we talk about today? So we said that the existing idea of putting attacks back in the training set works really, really well, right? And in fact, right, people have really trained ImageNet within just about the same amount of time training ImageNet. Normally, they train robust ImageNet classifiers, and they're very, very good. So we don't have a problem with it. Right. The trouble is we can't rigorously certify that they're actually robust. And existing techniques, they can't really make that guarantee. And they can't make that guarantee because they're either not expressive enough to really capture these attacks once they get large, or you can do mixed integer programming, and you can keep adding constraints, and you can split along the on-off status of ReLU, right? But then you might incur exponential time. You can't be both polynomial time and also sufficiently expressive, right? So here what we've shown is really we took the SDP relaxation and came up with a way to solve the SDP relaxation efficiently. That's one way of looking at it, right? So we took that surface of this shape, a very specific non-convex shape, right? And this particular shape, you can optimize the global optimality. And using this, we came up with the relaxation. Only preliminary work, we can really see that it's very, very good, right? And we think this might actually overcome the convex relaxation barrier. So it enjoys the tightness. It's actually tighter than the SDP relaxation. And it has the same order of variables as the original attack problem, right? It doesn't square the number of variables. It's still order n. Okay. Yes, algorithms right now, we have to use trust region algorithms. And because we have to use trust region algorithms, it's not great. It's still a little bit slow. Right? We also have work developing algorithms that will be linear time. So what we foresee probably in the next year or two is we foresee that there will be some way of solving this non-convex relaxation, right, in linear time, potentially using some SGD that's going to be extended version of existing methods to train neural networks. And using that, we're able to actually both empirically train ImageNet size neural networks to be robust, as well as to certify them using a similar optimization training algorithm. Right. So with that, I want to stop, and I want to thank you for your attention. I'll be very happy to take any questions. I would like to thank the sponsors of this research shown on the screen here. Thank you.
Thank you very much, Richard, for the very insightful talk. So we have a few questions in the Q&A. I can read them out, and I'll also allow the people who ask the questions to speak in case they have follow-ups. So the first question is from Andrew Stassel, who's asking, what is the cost relationship between the non-convex relaxation and the convex relaxation?
Yeah, so I think the shortest answer is, so existing convex relaxation, the best ones are linear programming based, and they take about cubic time to solve, right? They're not actually linear time because they're very complicated linear programs to solve. So they're cubic time. We're already cubic time, but we're hoping to get down to linear time, but using trust region algorithms, which also are actually could be used to solve linear programs, right? So similar algorithms right now, the time complexity is similar. In terms of tightness, as you saw, that we're able to achieve better tightness than existing linear programming relaxations.
The next question is from Tejesh, who is asking, could you elaborate on how exactly fictitious attacks are introduced during convex relaxation?
Yeah, so I mean, the original set of attacks is necessarily non-convex unless we have a very boring linear classifier that's literally linear. And if it's going to be non-convex, if we were to enclose it within a convex shape, then there will be points that do not originally lie within that non-convex shape that now lies within the enclosing convex shape, right? It's not possible to enclose a non-convex shape with a convex shape, right? It's not possible. So there will be points that didn't lie in the original set, and those points are not real. We can't realize them because, right, so the original non-convex set are all of the possible points that we can realize, and this point doesn't lie within it. So we can't realize this point, but if we reason about the convex set, then those points will become an issue.
Then we have another question from Jen, saying, are there any examples of these techniques being used in industry?
Can you clarify which techniques exactly you're talking about? Okay, let's move on to the next question.
Sure. The next question is asking, are you able to find true adversarial examples using the method? What if the optimal point is fictitious?
Yeah, that's a great question. So both mixed integer programming and things like simulated relaxation are on one hand able to find the true adversarial example, but on the other hand, struggle to do it, right? So we know with mixed integer program, how it really works is that it develops a lower bound, it finds progressively better upper bound. If they coincide, right? If they coincide, then you're done, and it gives you the true. But in most cases, they kind of converge to each other exponentially, and closing that last little bit of gap is extremely time consuming. In most cases, it's not really worthwhile. Same thing with semi-definite relaxations, right? So for very, very simple cases, it's exactly tight, right? Meaning that that lower bound is equal. And when the lower bound is equal, I think we saw in my slide that actually does correspond to a point on the original non-convex set, and that also generates an optimal attack. But if it's even slightly not tight, right? If it's loose by a slight margin, then you don't have the true attack, and neither does NILP, right? Neither does mixed integer programming. But in both cases, one would argue there's no point getting that true optimal attack, because using PGD, we can find an attack that is within, let's say, 0.01%, right, of this lower bound. And that point, this attack is not exactly globally optimal, but is close enough that we're not too bothered by the gap.
So maybe since we didn't answer Jen Marshall's question, I'll rephrase it.
Yeah.
So are there, for example, I guess computer vision is used in many applications like industrial robotics and autonomous driving features in cars, for example. So I guess maybe one could interpret her question as, could this be used, for example, to test the robustness of autonomous driving features, for example?
Yeah, so it's a great question. I think so. Ultimately, I hope, I believe, right? I believe this is going to happen. But right now, in this very moment, we're facing something like a cubic time complexity that we're trying to push down to linear. So until we hit linear, I'm hesitating to really give a definitive answer. But what I can say is, you have order n variables. There's no reason why you can't. You have order n variables and constraints, right? So there's no reason why you can't eventually hit linear time. So that's one. And two is, we're able to do an L2 adversary very, very easily, extremely tight, right? And using that L2 adversary, we can attach a generative model in front, right? And the generative model can be used to model the sorts of adversarial attacks that we actually see in computer vision, right? So you can imagine changing the tone of the image by a small amount will cause a dramatic pixel-wise change, right? But a small feature change. So we're able, right, to use an L2 perturbation to capture that with respect to the feature distance. And this technique will just come out of the box and be able to certify that. So I would say is right now we're working on getting this down to linear time, but once that happens, I think that this would be a relatively easy next step. Thank you.
Are there any other questions? Right, so let's thank the speaker, Richard, again for a wonderful talk, and see you all next week.
Thank you very much.
Thanks, Richard.